given, that's terrible. Sorry, I keep wanting to change how. Do let me know if things get off camera. I know the students in class do, but it's harder sometimes on screen. So let's say we're given some linear system of differential equations. And you can think of it very, very specifically as something like dx1 dt equal to, I don't know, let's say -6 x1 plus 0 x2, and dx2 dt equal to, what have I got here? I don't know, 5x1 minus 4x2. Or you can think of it more generally as just dx1 dt equal to something times x1 plus something times x2. And dx2 dt, again, equal to something times x1 plus something times x2. In either case, both of these are going to be represented with a matrix equation. So we could write this first one as the vector dx1 dt dx2 dt equal to the matrix -6, 0, 5, -4 times our variable. Or you can even write this more compactly as just dx dt, we're taking the derivative of the vector, and it's equal to a times x. Or for this one, the same sort of idea. Here we would have dx1 dt dx2 dt equal to the matrix a, b, c, d times x1, x2. Or again, writing this, right, we would really have the same formula. So you could write dx dt equal to, again, a times x. So what's the coefficient of the first equation for x1? For x1, the coefficient is -6. For x2, the coefficient is 0. Is that what you're asking about right there? Oh, yeah. The coefficient for x2 is 0. And that is a 0 right there. For this one over here, it's a b. That's clear. No problem. So typically, the kinds of things we can ask are, I can think of maybe 3 different types of questions that we often like to ask when we're given this. So the first type of question, or one of the types of questions, I shouldn't really say first, whatever. So one type of question could be determine the stability. So to determine, so let me use a slightly better word here. Yeah, determine the stability and type, I guess. And typically there are 6 possible answers to this question. You can be a stable node and unstable. So you can be a node, it's either stable or unstable. You can be a saddle. You can be a spiral that's stable or unstable. Actually, there's 3 spiral options. You can be stable, you can be unstable, and then you can also be a neutral spiral, which we haven't talked about any of the spirals yet. We're going to today, though. So there's typically 6 options for what kind of stability you can have. And then, what else? Oh, sorry, there's a couple of things. So we can also be asked to find the general solution, which is looking like our C1 e to the lambda 1 t times v1 plus C2 e to the lambda 2 t times v2. So, right, that's just finding the eigenvalues and eigenvectors. C1 e to the lambda 1 t times v1 plus C2 e to the lambda 2 t times v2. And then the third thing we are often asked to do is to, after you find the general solution, given some initial condition, so like, you know, the x1 of 0 is 5 and x2 of 0 is 3 or something like that. Given an initial condition, find the constants C1 and C2. I'm just kind of looking over your homework assignment, seeing if there's anything else that looks particularly different than that. And there's a couple other things, but these are most of the types of things we're usually asked to do. find out what kind of equilibrium we have, and then what the general solution looks like. Yeah, that seems pretty much like it. Cool. So let's look at some examples. Actually, let's look at this first example. So given this first example, we're going to answer all the questions. So usually we like to go straight from this, and that's a little blurry. Oh, it's a little better. So given something like this, we would rewrite it as, and I like to write it as dx dt equal to the matrix A. Okay, I would like everyone to type in the chat, what are the eigenvalues of this matrix? It should be really, really, really easy to type them. You can type to me privately so that not everyone sees your message, or you can type it just in the chat on your own. But everybody, yeah, I see some good potential answers from one person. How about everybody else? Do you guys agree? Maybe I'll have to make you do private next time. Yeah, that's exactly right. It is -6, -4. We know because it's a lower triangular matrix. So that makes it so the eigenvalues are just whatever is in the diagonal. Great, we've got the eigenvalues. Now, here's what I'll tell you. Lambda 1 and lambda 2, right? That's going to be -6, that's -4. Since they're both negative, we already know, or we will talk about how we can definitely classify that equilibrium right away. Since lambda 1 and lambda 2 are both negative, we know we have a stable node. And again, what you should think of when both eigenvalues are negative is, oh, along the eigenlines, everything is pointing inwards because negative eigenvalues point in towards the origin. And if everything's pointing in, you're stable because everything's going to push you towards the origin, towards both x1 being 0 and x2 being 0. Okay, so we can also find the general solution though. So now given this, we're going to find the eigenvectors as well. Eigenvectors are pretty straightforward to find here. We're going to say that we're going to find V1. So we're going to use lambda 1 and say that A times X should equal lambda 1 times X. We're actually writing it out. -6, 0, 5, -4 times, what have I got here? The vector that we're trying to find is equal to lambda 1, which is -6 times the vector that we're trying to find. And this one, we're going to get -6x1 equals -6x1, which isn't helpful, right? That doesn't tell us anything. It just tells us that x1 could be really anything. So then using the second equation, which we don't always have to do, but sometimes we do, 5x1 minus 4x2 equals -6x2. So 5x1 equals, let's see, -6 plus 4 is -2x2. And at this point, this is where I would do the thing where you say, okay, x1 is -2 and x2 is +5. That's what I want to do. Or you could solve for x2 and say x2 is equal to -5/2 x1. If you were drawing the eigenline, that would be your eigenline. Y equals -5/2 x is your eigenline. Typically, when we're doing this, if we're trying to graph stuff later on, we're thinking about x2 as the y thing and x1 is the x thing, right? If we're graphing this on an xy coordinate system, x2 is the vertical, x1 is the horizontal. Let's do the same thing and find v2. So we're going to have here -6, 0, 5, -4 times x1, x2 equals to -4 times x1, x2. And so here the first equation is giving us that x1 is equal to 0. So you're going to get -6 times x1 equal to -4 times x1. And then you're going to, I mean, you can bring everything to one side or not. You bring everything to the left, you get -2x1 equal to 0, which means x1 is equal to 0. And if x1 is 0, what does x2 have to be, everybody? Well, that's not really a great question. What do we usually pick? Right, thank you, Sarah, for answering very generally. Any number but 0 is the very, very correct answer, but the typical answer is 1. So there's our second eigenvector. So now we can totally write the general solution. The general solution to this system is going to be C1 e to the lambda 1 t times V1 plus C2 e to the lambda 2 t times V2, right? Just, you should definitely memorize that. So here it's going to be C1 e to the lambda 1 was -6 times V1, which is -2,5, plus C2 e to the lambda 2 is -4. t times v2, which was 0, 1. And let me actually look at one thing to be sure of something here really quick. Initial, solve the system. So I think it looks like most of the questions on your homework assignments have you finding particular solutions, right? They're almost always, if they're asking you to find the solution, they're giving you an initial condition and finding the specific solution here. So we should definitely do it that way. They give us an initial condition. Yeah. So that's what we're going to do. We're going to do that. So let's say we had an initial condition. So let's say that we're given, and it's pretty easy, especially, so I'll tell you all, we'll see right now that when one of your eigenvectors has a 0 in it, it's really easy to solve for C1 and C2. So let's say we're given the initial condition that x1 of 0 is equal to, let's make something weird like 9, not 9 in particular, and x2 of 0 is -5. And then we want to find C1 and C2. So given this initial condition, we want to find the particular solution. That is, we want to find C1 and C2. So whenever you're given an initial condition, you should always be thinking, oh, that probably means we're going to have to find the C1 and C2. Okay, so we're just going to take this equation and we're going to substitute in 0 for t and 9 for x1 and -5 for x2. And actually, so I left off a little bit here for my general solution. I should really be writing that this is what x1, x2 is equal to. That's the idea. Or really, I should say x1 of t, x2 of t. So what I do when I plug in t equal to 0, I get x1 of 0, x2 of 0, which is just the x1 value and the x2 value. And it's equal to C1 e to the 0 is 1. I don't think we really need to plug that in. So you get C1 times -25 plus C2 times e to the 0. That's why almost always, although not 100% of the time, your t value is just going to be 0 because it's going to be easy. Although they can give you an initial condition where t is equal to something else. We're going to C2 times 0, 1. So the nice thing about this situation here is it's really quick to solve for C2. I know, or actually I should say, sorry, for C1. They're both quick. So looking at the top row, what I really have is 9 equals -2 times C1 plus 0 times C2. Oh, great. C1's all by itself. That's why having a 0 in one of those spots makes it really easy to solve this. So I'm going to get that C1 is equal to -9/2, or if you prefer -4.5, totally fine. And then to find C2, I'll use the second equation. So the second equation is -5 equals C1 times 5 plus C2 times 1. So plugging in this value right there, we're going to get that -5 equals 5 times -9/2 plus C2. Or isolating C2, we get, I'm going to change this to -10/2, and I'm going to add 5 times +9/2 equals C2. So then -10 plus 45 is 35. So C is going to equal, sorry, C2 is going to equal 35/2. So now this is kind of like when you, or what I would say is, it's kind of like when you solve for the equation of the line and like you find the slope and then you go back and find B. And then after you find the B value, you then have to go back and plug back in what B is so that you can write the actual final equation of the line. Same idea is true here. We found C1 and C2. Now we have to go back and actually write the final particular solution. So all we're going to do is take this general solution and sub in, oh, sorry, not this general solution, apologies. This general solution and sub in C1 and C2. So our actual particular solution is, now I'm going to write this in 2 different ways. The way I like to write it, which is just writing it like this with the C1 and C2 values. So my particular solution is going to be x1 of t, x2 of t equal to -9/2 times e to the -6t times -2/5 plus 35/2. And again, if you prefer decimals, it's totally fine. E to the -4t times 0, 1. Now, that's not the way your web work homework typically asks you to write them. they kind of ask you to separate x1 and x2. So if I was actually trying to type this into web work, I would say, okay, well, my x1 is just the top part, the first entry in each of the vectors. So my x1 of t is just equal to -9/2 times e to the -6t times -2. That's going to be 9 e to the -6t plus 35/2 times e to the -4t times 0. That's not going to contribute anything. Also, I can check mentally right now, if I plug in 0 for t, x1 of 0 is definitely going to be 9, like it should be. And then x2 of t, same idea. We're plugging in, or not we're plugging in, we're just taking the bottom row. So the bottom row or the bottom entry is going to be -9/2 times 5, which is -45/2. I think it's allowed. Let me check one second. Yeah, just people looking for the other class. Okay, so we would look at the bottom row. -9/2 times 5 is -45/2 e to the -6t plus 35/2 times 2 is 35/2 e to the -4t. And these are the two things you would type in to web work for x1 and x2. And you also, we can double check just to be absolutely sure. If you plug in 0 for t here, you get -45/2 plus 35/2, which is -10/2, which is -5, which is the initial condition for x2. So it works. So questions about any of what we've done here so far? And if you want to say words instead of typing, you're more than welcome to. You don't have to. Okay. So let's look at a couple other things. Let's see. I want to do another example. So I feel like we've done a few examples like this. I think it might be worth, I think we should probably start getting into the imaginary solutions as well. So just as a reminder, so I know I said it last time, but I'm saying it again. But actually, let me just, instead of writing it all down again, really, let me just kind of point out, I'll tell you again, we have the following sort of things that happen. So if you have real eigenvalues, there are three possibilities. Both eigenvalues are positive. That's when you have an unstable node, also known as a source, and everything points outwards when both eigenvalues are positive. Or you can have both eigenvalues being negative, everything points inwards, you have a stable node or a sink. And lastly, thirdly, if the eigenvalues are opposite signs, that means one eigenline is going to be pointing away, one eigenline is pointing in, and that's when we have a saddle, which is also unstable. So we always consider a saddle to be unstable. There are some special things. Sometimes people look at, I doubt your teacher will focus. There's some other teachers for this class you don't have who focus on kind of these weird corner cases about when you have some interesting stability conditions. I don't think we have to worry about that, but if we do, we'll certainly address it. Cool. So, and actually just with this note, so we actually talked about this last, I can definitely post this on Canvas. This is also on Grant's website, but I'll post this on Canvas as well, just so in fact, I'll just toss it into the notes here like this. I just don't want to have to write it all out because it's the same thing over and over again. Not that I totally mind, but so the nice thing about this is sometimes if we're just asking about stability, you don't have to worry about finding all the other garbage. So for example, if someone said for the linear system of differential equations, where we have the usual setup, dx dt equal to a times x, where a is a 2x2 matrix. Analyze the stability of the equilibrium. Now, I should also point out that so far in all of these situations we are looking at, the equilibrium is just the origin. 0, 0 is the only equilibrium. Welcome, come on in, Erica. Been talking to the people over, but you're welcome to come on in. So we're just talking about stable, classifying systems of linear differential equations and seeing or how to classify the equilibrium. So I was just pointing out to everyone out there that if we look back at the original thing here, if you look back at this general linear system of differential equations, the only way that both these equations are going to equal 0 at the same time is if x1 and x2 are both equal to 0, which is the origin. So the origin is the only equilibrium for these types of systems. Later on, we'll see other equilibria. For now, but I should say later on, when we look at nonlinear systems of differential equations, then we'll see some other possible equilibria. But sorry. So we're going to analyze the stability of the origin. And it wholly depends on what our eigenvalues are. So for example, if our matrix was A equal to, say, -4, 2, -5, 3. So first of all, you should definitely get comfortable with recognizing that when someone writes down this matrix, they really mean a whole lot of other stuff. Right? When I write down this matrix, what I really mean is dx dt equals -4x plus 2y, and dy dt equals -5x plus 3y. Right? You don't need to write that down, but we need to know that that's what's being represented by this matrix. Or you can use dx1 and dx2, whichever way you want to do it. If I want to find the eigenvalues, so there's a couple ways of finding the eigenvalues. Let's just do it the normal way. So we're going to find the determinant A minus lambda I, which is just -4 minus lambda, 2, -5, 3 minus lambda. And if we take that, we're going to get -4 minus lambda times 3 minus lambda minus 2 times -5, which is equal to, let's see, I got lambda squared. I have a 4 lambda minus 3 lambda, so plus 1 lambda. I have a minus 12 and a plus 10, so that's a minus 2. So factoring that, I've got lambda plus 2 times lambda minus 1 equal to 0. So I have, in fact, lambda equal to -2 and lambda equal to +1. So here we would have a saddle because our eigenvalues are opposite signs. Now, something else that's kind of that's cool to know is that you only ever get a saddle if your determinant of your original matrix is negative. And they're real. So yeah, so if your eigenvalues are real and the determinant is negative, definitely going to be, actually, no, I take that back. You don't even, well, I mean, I should say, if the determinant's negative, it's going to be true that the eigenvalues are real. So yeah, I will just point out, cool fact, if the determinant of your original matrix is negative, that always means that we have a saddle. And we can talk about why later. One way of knowing this, and which is kind of cool, is actually the eigenvalues always multiply to the determinant of the matrix. So it's also true that the determinant of the matrix is equal to the product of the eigenvalues, which makes total sense, right? So if the eigenvalues are the opposite signs, if one's positive and one's negative, their product is positive or negative. Yeah, if one of them is negative and one of them is positive, then their product has to be negative, right? So the only way, but in any other situation, it's gonna be positive, right? If they're both positive, if they're both negative, positive. And later on, we'll see that even when they're imaginary, their product isn't negative. Their product also has to be positive, which is kind of cool. So the only way you get a negative product is when you have a saddle. And the only way you get a saddle is when you have a negative product, because that's when the determinant is negative. There's more to this, which we'll talk about. I don't imagine your teacher has said anything about this. Okay, I'll make sure. There's something I was gonna do. Also, just a minute, let me make sure everyone's got the attendance link. Cool. Yeah. So let's look at another example. Let's say our matrix was A equal to, what do we got here? 6, -4, -3, 5. And instead of using the determinant of A minus lambda I, I'm going to refer back to the trace determinant method, which is saying, okay, the trace of this matrix is 6 plus 5. It's just the sum of the diagonal elements. The determinant of this matrix is 6 times 5 minus -4 times -3, which is 30 minus 12, which is 18. I want to point out, this definitely does not have a saddle. because the product of the eigenvalues is positive. So they're either going to both be negative or both positive. Let's find out which. So I'm going to write the equation now. So remember, here's how the equation works. It's lambda squared minus the trace times lambda plus the determinant is equal to 0. You also could have gotten to this equation just the normal way by doing determinant of a minus lambda I. Set that equal to 0, it's going to factor as lambda minus 9 times lambda minus 2, which means our lambdas are both positive, which means we have an unstable node, also known as a source. Right. Because remember, right, when the eigenvalues are positive, the eigenline arrows point away from the origin, which is a really good way to think about it. Because if you think about pointing away as being unstable, that'll always kind of get you there the right way. And then remembering that the eigenlines do that sort of thing. Okay, let's look at one more example of this. Well, for now anyway. Let's say our matrix was A equal to 0, -2, -1, 3. And so again, actually, sorry, that's not the one I want. Oh, sorry, well, we'll do this one, sure. We can do this one first, even though it's not the one I want to do first. So we do this one. Again, I'm going to use the trace determinant method. Actually, I'm going to do it both ways. So trace determinant. So we have that the trace is 0 plus 3, and the determinant is 0 times 3 minus -2 times -1, which is equal to -2. Which, since it's negative, we can automatically conclude that we're going to have a saddle. We'll still do more work, but I just want to point out that this determinant being negative means we have a saddle for sure 100% of the time, which is great. Well, let's do a little bit more. So our polynomial would look like lambda squared minus 3 times lambda minus 2 equal to 0. Or if you prefer, you could have done it the other way and said determinant of a minus lambda I is the determinant of this matrix. Which ends up being negative lambda times 3 minus lambda minus -2 times -1, which is going to be lambda squared minus 3 lambda. Oh yeah, it's the same as it should be, right? There isn't this, it's not like it's a surprise here, right? It's always going to be the same whether you do it the trace determinant way or the usual determinant of a minus lambda I way. I've just seen over the years that this can be really easy to calculate, whereas this other thing can be easy to kind of make a mistake with. Bummer, it doesn't factor. So this is actually why it's nice to know this thing about the determinant, because if they're just asking us to classify, we'd be like, oh, well, I know if the determinant's negative, then my eigenvalues are going to be opposite signs and I'm going to have a saddle. But we could also use the quadratic formula to see this. The quadratic formula is going to tell me that my eigenvalues are going to be -b plus or minus the square root of b squared minus 4 times a times c all over 2 times a, which ends up being 3 plus or minus the square root of, let's see, 9 minus 4 times -2 is +8, and 9 plus 8 is 17. So we have 3 plus root 17, which is positive, and 3 minus root 17, which is negative. So this is a positive eigenvalue and a negative eigenvalue, which means we have a saddle again. What you might eventually end up seeing, depending if we get there, is that there's a way of looking at just the determinant and the trace of a matrix and using only that information, not really doing anything else to determine if we have a saddle or a source or a sink or a spiral or whatever. Welcome, come on in. It's a very virtual class today. So let's do one more. I know I said that last time, but I really mean it this time. So let's say that this matrix is, what do we got here? -3, -1, 1, -6. So let's see, if I find Again, I like trace determinant. I'm a big fan. So the trace, actually, let me ask all you, what's the trace? Type it in the chat. What is the trace? You all can write it down. As far as matrices go, the trace is kind of like the fastest thing you can find. Yeah, that's right. Trace is definitely -3 plus -6, which is -9. For sure. The determinant is a little more work. The determinant is -3 times -6 minus -1 times 1, which is +18 plus 1, which is 19. Now, there is kind of a trick here, which I'm going to tell you, is that if your eigenvalues are real, which is the whole thing, but if your eigenvalues are real, then if the determinant is negative, then we know that we have opposite values in the saddle. If the determinant is positive, then if the trace ends up being, I have to say the right words here. If the trace ends up being, I need to think about what's happening here. Let me see here. Yeah, sorry, brain. Well, let's actually look at this previous example. In this previous example, the trace was positive, and that's not a good example, James. Let's look at the previous example. Sorry. In the previous example, the trace was positive, and the eigenvalues were both positive, and we had instability. Over here, I'm going to bet that the trace being negative is going to lead to both of our eigenvalues being negative. Let's take a look and see though. So again, I have this equation, lambda squared plus 9 lambda plus 19 equal to 0. And once again, this doesn't factor, right? There's only one way to multiply the 19, well, there's two ways to multiply the 19, but they don't work. So we have to use the quadratic formula. So we're going to get that lambda equals -9 plus or minus the square root of 9 squared minus, okay, close call here. 4 times 1 times 19 over 2 times 1. 4 times 20 is 80, so 4 times 19 is 4 less than 80, which is 76. This is -9 plus or minus the square root of 76 all over 2. So for sure, one of these eigenvalues is negative. -9 minus the square root of 76 all over 2 is for sure a negative number. But it's also true that -9 plus the square root of 76 divided by 2 is also negative. And the reason why is because 9 is a bigger number than the square root of 76. So 9 is the square root of 81. So -9 plus a number that isn't quite 81 is still going to be negative. If they're both negative, that means we have a stable node, also known as a sink. Cool. And I'll point out that our trace was negative here, and our eigenvalues were negative. And before, when our trace was positive, our eigenvalues were positive. So if they're going to be the same sign eigenvalues, the trace tells you what sign they're going to be, which is kind of cool. There's a whole thing that I'm alluding to, kind of, not really alluding to, but like building up, that we're going to talk about at some point. Maybe not today though. Okay, so that's kind of it as far as it goes for if you're just asked to use the eigenvalues to classify your stability of equilibrium. This is all there is to say, is if your eigenvalues are real. But there's this whole other situation that can happen where the eigenvalues might not be real. So let's take a look at that. And actually, before we can take a look at that, we need to build up a little bit of machinery here. So let me grab this. So there's a really, really, really important mathematical identity that you may or may not be aware of. I feel like it might have come up in 17b, but it might not have. So this is called Euler's identity. And yes, his name is pronounced Euler. Although people often like to say Euler, but it is pronounced Euler. I was the other day, not really, but you know, like how you ever see you ever listen to the news and like Reuters news source? It's spelled Reuters and it's pronounced Reuters. It's the same kind of idea. This EU has like an oi sound, so this is Euler, just like Reuters is Reuters. Anyway, I finally made that connection a couple of days. I was like, oh, that's neat. I never thought about that, but super cool. Anyway, the identity is the following: e to the I times t where I is the imaginary number square root of -1, is equal to cosine of t plus I times sine of t. So you might ask, why is this true? Because it seems kind of bonkers that e to the I, right? Oh, and I should write down, right? And just as a reminder, I is equal to the square root of -1. So I'm going to remind you some things that I feel like, did we learn about Taylor polynomials in 17a? You may or may not have. It's okay if you didn't. So it's kind of like a Taylor polynomial or a Maclaurin series is a way of expressing a function as an infinite sum of powers of x. So let me write down a few for you, and I'm just gonna, I might show you something kind of cool. So for example, it is true that sine of x is equal, and you don't need to write all this down if you don't want to, you're welcome to, but writing this down is probably not super important. Sine of x is x minus x cubed over 3 factorial plus x to the fifth over 5 factorial, et cetera, et cetera, et cetera. Forever. Now, this is actually pretty neat. If you actually start graphing this, you can kind of see what we mean. So let me just show you all really quick, because I think it's super cool to actually understand what we're doing with this. So, come on. What are you doing? Give me the thing. So really quickly here. So here's good old sine of x. And now you might not think my Taylor polynomial is so good, but just wait a minute. So first of all, the thing we started with was just x. Okay, not a very good approximation of sine of x so far. So let's make it a little bit better. Let's put on the next term, and we're going to subtract x to the third divided by, whoops, not that, x to the third divided by 3 factorial is equal to 6. Oh, look, that looks a little bit better, right? It's a good approximation, at least for a little bit. And if we add on the next term, which is x to the fifth divided by 5 factorial, which is 120, even better. And so the more, every time you keep adding on terms, you just get closer and closer to being a better approximation of this function. 7 factorial, I don't know. It should work. So look at that. If you zoom in, at least, from like -3 to 3, it's a very good approximation. It starts being less so as you get past like 4, but the more terms you add, the better and better this approximation gets. So that's the idea, is that if you actually did this forever, they're not just approximately the same, they're actually the same, which is super cool. And we can find cosine, and let me show you how we're going to find cosine. What's the derivative of sine? Cosine. So if I take the derivative of sine, I get cosine, and the derivative of x is 1. And the derivative of x cubed is 3x squared. But I want to point out, not on this piece of paper, that 3 divided by 3 factorial is 3 divided by 3 times 2 times 1, and the 3's cancel, and you get 1 over 2 factorial. So 3 over 3 factorial is really just 1 over 2 factorial. So you get x squared over 2 factorial. What do you all think this next term is going to be? If I take the derivative of x to the fifth, I'm going to get 5x to the fourth, and the 5 is going to cancel, and I'm going to be left with on the bottom 4 factorial, right? Because it would be, right, I would have 5x to the fourth over 5 factorial, which is 5 times 4 times 3 times 2 times 1, but then the 5's cancel, and you're left with x to the fourth over 4 times 3 times 2 times 1, which is just x to the fourth over 4 factorial. So the nice thing about the sine and cosine in this thing is that their patterns are very similar. Sine is every odd power of x, where the terms alternate positive, negative, and the denominators are just the same as the power of the factorial. Cosine, same deal, except they're all even. And then the last one we need is that e to the x is all the terms divided by their own factorial, but all positive. So e to the x is 1 plus x squared divided by 2 factorial plus x cubed divided by 3 factorial, et cetera, et cetera, et cetera. Okay, so you might, again, like, why do we care? Well, we're about to see. So You may have seen this in 17A. You may not have seen this in 17A. Either way, it's true. Either way, all we're going to do is just see it right now and then kind of forget about it. Really. The other thing we need to know before we do this is that if I is equal to the square root of -1, I squared is the square root of -1 squared, which is -1. I cubed is I times I squared, which is I times -1 or -I. And I to the fourth is I squared times I squared, which is -1 times -1, which is 1. And then after that, you're kind of back at where you started. If you do I to the fifth, it's really just I times I to the fourth. I to the fourth is 1, so it's really just I. So you're back in the same cycle where after I to the fifth, you just go back up here and like, oh, I to the sixth is really just I squared, which is just I squared, which is -1. Oh, excuse me. And so on. I to the seventh is the next term, which is -I. Okay, now, finally, here's what we're going to do. We're going to take e to the x, and we're going to replace the x in each of these spots here with an I times t. So check this out. E to the I times t is going to be 1 plus I times t plus I times t squared over 2 factorial plus I times t cubed over 3 factorial plus I times t to the fourth over 4 factorial, and so on and so on and so on. Okay, so now I'm going to break this up. I've got I times t. What's I squared? -1. So I really have a minus t squared over 2 factorial. I cubed is -I, so I have a minus I times t cubed over 3 factorial. I to the fourth is +1. So we'll have a plus t to the fourth over 4 factorial. And the pattern is going to repeat. The next term would be plus, this would be an I, right? Because I'm back to the beginning of the pattern. An I times t to the fifth over 5 factorial. The next term would be a minus t to the sixth over 6 factorial. The next term would be a minus I t to the seventh over 7 factorial. The next term would be a plus t to the eighth over 8 factorial. Now check this out. Here's all my I terms, all my not I terms. All those terms don't have an I in them. Oh, look, those are all the even terms, like all the things that are showing up in cosine. So here's what we've got. We've got 1 minus t squared over 2 factorial plus t to the fourth over 4 factorial minus t to the sixth over 6 factorial, et cetera, et cetera, et cetera. And then the I things, if I factor out an I, I'm left with t minus t cubed over 3 factorial plus t to the fifth over 5 factorial minus t to the seventh over 7 factorial, et cetera, et cetera, et cetera. But that's exactly cosine of t, and that's exactly I times. So that's the whole kind of deal. That is why this works. Which is neat. I mean, anything else notwithstanding, this is a neat thing to know. I will also tell you that it's where one of the most famous equations in math comes from. You might have heard of someone saying at some point, e to the I pi equals 0 minus 1. You might not have. So just to point out, if you plug that in, or if you plug in t equals pi, you get e to the I pi equals cosine of pi plus I times sine of pi. But cosine of pi is -1, and sine of pi is 0. So you end up getting e to the I pi equals -1, which people then like to write as, I think it's silly to write it as this way. Some people write it as e to the I pi equals 0 minus 1. I think it's better to write it as e to the I pi plus 1 equals 0. And the reason this is a famous math equation is because it contains all 5 of like the most used mathematical numbers, e, I, pi, 0, and 1. And those are all kind of very famous, important math numbers. So again, not super important for this class, but it was the opportunity to say it. So I feel like I should tell you all that there's a cool formula here. Okay, so, but what we're really going to do with this is the following. So yeah, we'll do that. Cool, cool. So let's go ahead and look at this next situation. So I will hopefully in this class, we're not going to be doing too much of finding eigenvectors that go with imaginary eigenvalues because they're kind of gross. But we might have to, and we'll talk about it when we get there if we have to. Which equation? So we never really have to use Euler's identity, most likely. But so the point of talking about it really is that we're going to use it to kind of see why we have the shape that we have for the stability of the point of the origin of our equilibrium. That's what, yeah. So let's say we want to classify the stability of the origin of our equilibrium for the following system. dx dt is equal to negative x plus 2y, and dy dt is equal to negative 3x minus y. And we'll even throw in some initial conditions just for fun. X of 0 is 2, y of 0 is 0. So let's do the usual thing. We'll write our matrix. Our matrix is just negative 1, 2, negative 3, negative 1. So I'm going to try to keep hitting you with the trace determinant method just because I think it's worthwhile, but we'll look at this both ways. So determinant of A minus lambda I, you're going to get negative 1 minus lambda, 2, negative 3, negative 1 minus lambda. And we multiply this out, we get negative 1 minus lambda times negative 1 minus lambda minus 2 times negative 3, which ends up being lambda squared plus 2 lambda plus 1 plus 6, which is lambda squared, plus 2 lambda plus 7 equal to 0. Which I'll point out totally goes with doing the other way. Here, the trace would be negative 1 plus negative 1, which is negative 2. And the determinant is negative 1 times negative 1 minus 2 times negative 3, which is 1 plus 6, which is 7. Which totally leads you right to there. Now, what's terrible about this is our eigenvalues are going to be imaginary. We can find them. So we can't factor that for sure. We're going to be using a lot of quadratic formula. And actually, this is where I'm going to say the trace determinant thing actually really comes into play. So you can totally find this equation and then find the quadratic formula. But I want to point out, and this is kind of important, maybe important. So when you're finding this determinant of A minus lambda I in general, the determinant of A minus lambda I for a 2x2 matrix is always going to equal lambda squared minus the trace times lambda plus the determinant. So if we're setting that equal to 0, we can just throw those things into the quadratic formula, right? Your negative trace is your B and your determinant is your C. And one is, your A. So if I was trying to just use the quadratic formula here, I'd say, the lambda is negative trace plus or minus the square root of the negative trace squared minus 4 times 1 times the determinant all over 2. We're writing this a little more nicely. The trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2. So what's nice about this is you can jump straight from seeing the trace and the determinant to what the eigenvalues are going to be, which I think is nice. You don't actually have to write out the quadratic, but you can. So here, our eigenvalues are going to equal the trace, which is negative 2 or negative B, plus or minus the square root of the trace squared minus 4 times the determinant all over 2. And we can observe, that discriminant, that thing inside the square root there is definitely a negative number. So this is going to equal negative 2 plus or minus the square root of 4 minus 28 is negative 24 all over 2. Which you may or may not want to simplify. We should probably simplify it. This is -2 plus or minus. The square root of 24 is 4 times, or I should say 24 is 4 times 6, and the square root of 4 is 2. So we can write this as 2i square root of 6. I for the negative part that we're taking care of, and the 2 because the square root of 2, or I should say 2 is the square root of 4, and 4 times 6 is 24. And then we can divide each part by 2 and say their eigenvalues are -1 plus or minus I root 6. So those are our eigenvalues. And what I want to point out is they are neither positive nor negative. Right? When you start talking about things being complex, there is no sign really. I mean, we still have each part you can say has a sign, but in general, a complex number is not positive or negative. It's because there's an imaginary part. Yeah, positive or negative really refers to being specifically on the real number line. And once you add an imaginary part, you're no longer on the. So, a couple things to see here. Our eigenvalues are -1 plus I root 6 and -1 minus I root 6. And what we should say are a couple things. So, thing one, these eigenvalues are always going to be complex conjugates. All that means is that in one of the eigenvalues, you'll have the real part plus the imaginary part. And in the other eigenvalue, you'll have the same real part minus the same imaginary part. And even better, in these kinds of situations, and when you're finding roots of polynomials in general, if they're imaginary, they always come in complex conjugate pairs. Which makes sense if you think about the quadratic formula. You're always going to get this real part plus or minus the square root part, which is where the imaginary part's coming from. So they're always going to come. And then the other thing that's really worth noting is what the real part and the imaginary part are. So in this one, we often write our eigenvalues as generally a plus or minus b times I, where a is the real part. That's the real part. And b is the imaginary part. And I'll say sometimes people get a little hand wavy with how they talk about it. So it is probably correct either way to say that the imaginary part of this eigenvalue is the square root of 6, or that the imaginary part of this eigenvalue is I times the square root of 6. Sometimes people include the I, sometimes they don't. I've never been able to nail anyone down on really why we do it one way or the other. I personally would say that the imaginary part of this eigenvalue is the square root of 6. The imaginary part of this eigenvalue is the negative square root of 6. This is a negative right there. Okay. So here's what's going to happen, or here's what could happen. We could try to write the system of solutions, and the system of solutions works kind of the same way, except it's way, way worse. So again, I'm kind of hoping we're not going to have to deal with it, but we might have to. But the idea is the same idea, that our general solution, x of t, y of t, is equal to c1 e to the lambda 1 t times v1 plus c2 e to the lambda 2 t times v2. And in this case, that's going to be c1 e to the, okay, lambda 1 is, what my eigenvalues again? Let's see, let me write them down over here. I forgot what they were. -1 plus I root 6 times whatever the eigenvector is. And I will tell you, the imaginary eigenvectors are gross. We're probably not going to find them unless we have to. And then c2 e to the lambda 2t, which is -1 minus I root 6 times t. I forgot the t up here, sorry. v2. One thing. Yeah. Cool. Sorry, I'm looking at one little thing here. So what's going to happen here is that this is where we're going to use the idea of Euler's theorem, Euler's formula, which is that this e to the I plus e to the -1 plus I root 6, take a look at this. So this is going to become c1 e to, I'm going to distribute the t here. So just watch this carefully for a moment. It's going to be e to the negative t, and then instead of saying plus t I root 6, I'm going to say it's times e to the I root 6 times t. Right, same thing. I can add those powers together and get back to that. plus C2 e to the negative 1 times t is negative t, and then e to the negative I root 6 times t is negative I root 6 times t. Okay, but check this out. Euler's formula says that if you've got e to the I times something, right, just like previous, like back before, right, e to the I times t is cosine of t plus I sine of t. So e to the I times the square root of 6t is going to be cosine of the square root of 6t plus I times sine of the square root of 6t. And similarly, e to the negative I square root of 6t is going to be cosine of negative root 6t plus I sine of negative root 6t. What happens is this causes an oscillation. So if you think about graphing this, or I should say, no, that's fine. Yeah. If you think about kind of what's going to happen as t goes on, you're going to get oscillating back and forth. As t gets bigger and bigger. So as t gets bigger and bigger and bigger and bigger, this value is going to go between negative 1 and 1, and this value is going to go between negative 1 and 1. So what's going to happen is we're going to get this kind of spiral effect where you're going to get larger and larger values as time goes on, or smaller and smaller values, but they're going to bounce back and forth. So we have this kind of deal here. We have the x as a function of time is doing this sort of, well, in fact, we know that from our initial condition way back here, x of 0 is 2. So x is starting at 2, but then it's having this oscillating behavior. And also, I should say, not just oscillate, but also they're going to get smaller, not bigger in this case, because we have a negative, we don't have a negative eigenvalue, we have an eigenvalue with a negative real part, which corresponds to this right here. And think about it, if you have e to the negative t, as time goes on, e to the negative t gets smaller and smaller and smaller. So normally, if we just had e to the negative t, we'd be like, oh, it's just going to go down from left to right. But since it's e to the negative t times this thing that's going to oscillate up and down based on where we are, it's going to do this kind of deal. Like that. And in a similar way, y of t well, y of t, we said the initial condition was 0. It's going to oscillate in a similar sort of way, but still dampening because the y part also has a negative real part. So that's kind of what's going to happen. So if we look at this, so at the beginning, x is 2 and y is 0. And then x doesn't just get smaller, it gets, both start to get smaller. But then at some point, x actually goes back and gets bigger and y gets bigger. So there's kind of this like x getting smaller, 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 and then y coming back, or x going over. Kind of like this. And so what I'm trying to say with too many words here is, here's what's going to happen. If we start, say, at the point where x is 2 and y is 0, well, looking at what our oscillating is going to do here, x is going to get smaller and y is going to get smaller. So we're going to go this way. X getting smaller and y getting smaller. But eventually, we get to like these troughs here, and x and y are both going to turn around. Maybe not at the same point, but eventually we're going to get to like this maybe bottom here, and then y is going to start getting bigger, right? Maybe y starts getting bigger before x does. So y starts getting bigger, and then we come around here, and oh, now we've gotten over to maybe like this spot here, which corresponds to this spot here. Now x is getting bigger while y is still getting bigger. So we've got this spiraling behavior. And we know it's spiraling inwards because overall, the distance that our values are from 0 is getting smaller and smaller and smaller. Okay, I know we've said a lot of stuff here. Here's the takeaway. If our eigenvalues are imaginary, or I should say complex, then the equilibrium has a spiral behavior. And in this case, it's a stable spiral because as time goes on, we move towards the equilibrium. So this example, and we're going this way, right? We're going inward. This is a stable spiral. Now, what I point out is that even though the eigenvalues themselves aren't negative, the real parts of these complex eigenvalues are negative. So the eigenvalues, once again, were -1 plus or minus I times the square root of 6. And the real part being negative is what's going to tell us that we have a stable spiral. It's a spiral because the eigenvalues are complex. It's stable because the real part is negative. So let me ask you then, if we had a system where the eigenvalues were complex but the real part was positive, what might you expect to happen? Unstable, meaning it's not going to spiral inwards, it's going to spiral outwards. So we can look at another example as well. In fact, let's just actually write down the criteria. So here are the things that are going to happen. If you have so I should say for complex eigenvalues, meaning lambda is equal to a plus or minus b times I. So if the real part b is positive, so b greater than 0, that's not the real part. Who let me write that? Sorry, that's not right. I apologize. The real part is not b. B is the imaginary part. Let me just start over. Sorry. Let me say that again. Complex eigenvalues. So if lambda is equal to a plus bi or a minus bi, then let's just say the real part is a, the imaginary part is b. And we have three things that can happen. So if a is positive, if the real part is positive, then we have an unstable spiral. Meaning an outward spiral. And what's going to happen here is, so what's happening here is, unlike the previous one, right? In our solution, in the previous one, we had, sorry, here. We had e to the negative t times e to the imaginary part. Well, now that e to the negative t is going to be e to the something positive times t. And so instead of the values getting smaller as time goes on, the values get larger as time goes on. So in that case, since a is greater than 0, our e to the a plus or minus bi is going to be e to the a times e to the plus or minus bi. And this part here, that's the Euler part. It gives you the oscillation. And this part here is the part that's either, oh, sorry, I forgot the t. This part here is going to be the part that grows since a is greater than 0. Or you can have the other situation we saw just now, which is that if a is less than 0, then we have a stable spiral or an inward spiral, meaning we're getting closer and closer to the origin. So in this case, we have, again, e to the a plus or minus bi times t, which is e to the at times e to the plus or minus bi times t. And now, since a is negative, this part is dampening or getting closer and closer to 0. And this part's still the oscillating part. Finally, there's one last thing that can happen. It doesn't happen very often, but if you happen to have a purely imaginary eigenvalue, so if the real part is 0, then we have what's called I think we call it a center or a neutral spiral. . So this spiral doesn't spiral inward or outward. It spirals back on itself every time. So you just keep getting this kind of loop. In other words, it kind of like it looks kind of like a circle, more like an oval actually. But yeah, you've got this circle where you're not getting closer to the origin, you're not getting further away from the origin. You're just doing the same thing over and over and over again. And it's because, right, you're not getting a dampening effect or a growing effect. You're just getting the e to the plus or minus bi times t part, which means you're just getting the oscillating part. So now we can fully determine the stability or instability, or what kind of stability or instability of our system just by looking at the eigenvalues. If the eigenvalues are real, both positive, unstable, both negative, stable, one of each, saddle. If the I should have said stable node, unstable node. If the eigenvalues are complex, if the real part's positive, unstable spiral. If the real part's negative, stable spiral. If the real part's zero, we have a neutral. So then you can just say, here's a matrix, or here's a system of equations represented by a matrix. So for example, if we have A equal to 2, -5, 2, 1, which corresponds to the system dx dt, dy dt. Dx dt is equal to 2x minus 5y. Dy dt is equal to 2x plus y. Classify the stability of the origin. And really our only job here is to find the eigenvalues. Once we find the eigenvalues, we're pretty much done. There's one, actually, we're not quite done because there's one other thing we're talking about, but we're almost done. So let's see. So eigenvalues, okay, I'm gonna do it the other way. My trace is 2 plus 1. My determinant is 2 times 1 minus -5 times 2. It's 2 plus 10, which is 12. Oh, bummer. If it'd been negative, I would have had a saddle. I do want to encourage you to take that to heart. If your determinant is negative, saddle all the way. Kind of great. Yeah, I'll say more about that in a second. So using my, so here's where I'm kind of cheating, not cheating, but I'm using that I know what's going to happen. I know this is going to not factor in. Normally, if I was doing this, I probably would have tried to write it as a polynomial factor. But I will say you can always just jump straight to the quadratic formula. You know, be like, okay, it's going to be trace plus, or is it trace or is it negative? I always forget. I gotta be honest. I forget if it's the trace or it's the negative trace. I know I could actually figure it out, but I just want to go back and look. Like, no, it is the trace. Yeah, it's the trace. It is. Cool. That's what I thought. All right. Trace plus or minus the square root of the trace squared minus 4 times the determinant all over 2. So let me just point out one quick thing by looking at this formula. Let me ask you all. If the determinant is negative, could the inside of this square root ever be negative? No, it couldn't, right? Because you'd have a negative and a negative, which is positive, and a positive here adds that. So I just want to really emphasize, if the determinant is negative, the eigenvalues have to be positive, real, and then you get one of each side. Super cool. It's not the case here, though. So in this case, we get 3 plus or minus the square root of 3 squared minus 4 times 12 all over 2, which is 3 plus or minus the square root of, I don't really care at this point, but it's 9 minus 48, which is negative 39. So here's all I really, really care to take away from this. 1, my eigenvalues are not real, they're complex. 2, the real part is positive or negative. It's positive, right? Because you've got a 3 over 2. I didn't even care about the 2 there. I've got a 3. So notice, for complex eigenvalues, the real part really just corresponds to whether the trace is positive or negative. If the trace is positive, the real part's positive. If the trace is negative, the real part's negative. So the real part is positive. Great, those two things together mean we have an stable spiral. Now, there is one other question that people like to ask, and that is, what direction is your spiral turning? Is it turning clockwise or turning counterclockwise? And I remember looking this up back when I first taught this class, or was helping with this class. I was like, I have no idea how to figure that out. There is a way that you can tell by looking at the matrix that I have like a little sticky note on my computer that says if it's positive up here, it goes one way. If it's positive down here, it goes the other way. I don't remember what it is though, because I literally can't commit to memory. So what I will say is there is a way to tell that if you have, so first of all, if you have complex eigenvalues, it is true that these two things have to have opposite signs. You can do some analysis on the matrix, but I'll just tell you it's true. These have to be opposite signs. So if those are opposite signs, one of them is positive, one's negative, or the other way. And there's something like, we'll figure it out right now. So here's the easier way to do it, where you don't have to memorize something that's, for me, impossible to memorize. You start drawing stuff. So I'm going to take my actual system of differential equations. I'm going to plug in like maybe 2 points, maybe a few more than 2, I don't know. So I'm going to pick, I usually like to pick these points, 1, 1, -1, -1, -1, 1, and 1, -1. So, and I've got dx dt equal to 2x minus 5y, dy dt equal to 2x plus y. So if I pick the point 1, 1, I get that dx dt is equal to 2 minus 5, which is -3, and dy dt is equal to 2 plus 1, which is 3. So at the point 1, 1, I'm pointing left because dx dt is negative, and up because dy dt is positive. And it's also in the same amount. So I'm specifically pointing exactly up and to the left, meaning you can say I'm pointing what? Northwest, if you like. I'm going exactly up and to the left. I have enough information right now to know this is counterclockwise, because I'm going up and to the left from there. Now it's a little harder to tell if the thing you get like points kind of like inward. It's a little harder to tell. But here's what I would say. It's actually kind of cool. It took a while to figure this out, but I think it works. If you look at the line y equals x, if you pick the point 1, 1, if your vector points anything on this side of that line, it's going counterclockwise. If your vector points anything on this side of that line, it's going clockwise. Even if it looks really kind of silly and like it's pointing like this, like it's pointing like that, I'd still be going clockwise because I'm going down around the origin instead of left around. So that's the way I kind of think of it. We could plug in more points though to really kind of verify this. So if I plug in the point -1, 1, I get dx dt equal to -2 minus 5, which is -7, and dy dt equal to -2 plus 1, which is -1. And so then from the point -1, 1, I'm going way more left than I am going down. My vector is mostly to the left, but a little bit down. So it kind of looks like that. Still looking like counterclockwise. Oh, we should wrap it up. Oh, we got a couple minutes. So then, right, you could continue. So basically, you should draw as many little vectors as you need until you can determine if it's clockwise or counterclockwise. And again, that's only going to, so if it's a spiral, it has to be one of these two directions. So only if it's a spiral, meaning only if you have complex eigenvalues, and you're asked, and you definitely are in your homework. I saw plenty of questions where you asked to find the direction of your spiral. You just start drawing little things. Now, I will point out, looking at this now, I know it's true that if your matrix looks like this, so I should say if your eigenvalues are complex and your matrix looks like this, where you have a negative number here and a positive number here, then it's definitely going to be counterclockwise. On the other hand, that must mean that the opposite, where it's positive here and negative here, is going to be clockwise. But that's only true if the eigenvalues were imaginary to start off with. If they're real, there's no talk about clockwise, counterclockwise at all. Right, you would have a node or a saddle. Something else I want to mention here. I guess not. I feel that's good. But here's what I'd say. I would say, don't memorize this. I mean, it might be useful like when you're trying to do this problem, but really the idea is that if you're asked this on the test, saying this because I memorized it is not going to be a good answer. Saying this because I drew a picture and I can show you that it's either going counterclockwise or clockwise is the much better justification of what's happening. Unless your teacher says do something else. All right, let's wrap it up. I will be over in CADS. Have a lovely Halloween. I will see you on November 1st. I know, right? Time just, you know what? I feel you. You wouldn't believe how I feel about the time. Oh, yeah. It really does go by fast. I should stop this. See y'all later. Thanks for coming on Zoom and participating. I do appreciate it. See y'all next time.